Hi, my name is Kennedy Rand, and this is my Lab 5 video report on Faraday's Law. The purpose of this lab was to observe the difference between a magnet falling through a non-ferrous tube and a magnet falling in freefall. After collecting data, this lab will allow us to model the system through our code and compare our actual results to the simulated results. My actual results when dropping the magnet through the tube was an average of 1.65 seconds, and the simulated time was 1.828 seconds. So to carry out this lab, we had to use several fundamental principles of physics. The first one being Faraday's law to find the current in each small ring of the tube using this equation. The Biot-Savart law to find the magnetic field and force on each current carrying ring using this equation. And then we use Newton's second law to update the position and velocity of the magnet in the code, and Newton's third law to find the force exerted on the falling magnet by the tube of rings. So to carry out the experiment, we had several materials and a whole set of methodology to carry out. So the materials were a roll of aluminum foil, a bar magnet, a smartphone, and a tool to measure the dimensions of the tube. And then the process was to suspend the roll of aluminum in the air so that you will be able to see the magnet when it exits the tube, and then suspend the magnet above the roll, frame the smartphone camera so that the entire setup is in view, and press record, and then drop the magnet through the tube. So my observations were that I originally expected the magnet to fall through the tube very quickly, but it did experience some resistance and fell slower than I initially expected. The magnet also exits the tube the same way that it entered, which was vertically. And here is a video of the process, which I used to get the times in the next piece. So here, after running the experiment, I was able to arrive at these values. On the top are my measurements for the dimensions of my aluminum tube, and the bottom chart shows the different times it took the magnet to fall through the tube over 5 trials. The average was 1.65 seconds, and the magnetic dipole moment of my magnet from my previous lab was 2.24. The next step of the experiment was to use code to create a simulation of the experiment. In the first part of the code, going in order of the arrows, I initialized my constants, set up the simulation to see the tube of foil as a series of rings, and then actually created the aluminum tube and the simulation of the falling magnet. Next, I created the magnet at rest using my mu-mag from the previous lab and created functions to calculate the magnetic field and d-flux over dt. Next, I created a visual output to view the simulation of the magnet falling through the tube. The code on the right shows the calculations for current in each ring, magnetic field of each ring, and the total magnetic force acting on the magnet. Finally, this last chunk of code updates the net force, velocity, and position of the magnet inside the while loop. The while loop is set to run until the magnet has entirely exited the tube, so this chunk of code will be repeatedly updated through the simulation. On the right, you can see the final graph output of velocity versus time from running this code. So here you can see a screen recording of the simulation and creation of my graph. The cylinder represents the tube of foil, the red rings represent increasing current below the magnet, and the blue represents decreasing current above the magnet. We can see that the magnet takes 1.828 seconds to fall through the tube in the simulation. In conclusion, we can determine that dropping a magnet in free fall would cause the magnet to fall much faster than it does through the aluminum tube, as there would be no magnetic force resisting the fall. In comparing my results from the actual experiment versus the simulation, we see a small 9.74% error. This error could be due to either error in my experimentation or due to error in calculating the magnetic dipole moment of my magnet from Lab 3. Finally, if the resistivity of the conductor were reduced, the induced current would be much larger than the gravitational force, and the magnet would fall through very slowly, if at all. And if holes were cut into the tube, they would reduce the number of complete rings making up the tube, which would weaken the induced current and magnetic field. The magnet would thus fall much faster. Thank you.